In this example, we're going to look at a gas phase reaction in an adiabatic plug flow reactor. It's a first order reaction. The rate constant depends exponentially on temperature. And we're given feed conditions, heat of reaction, and heat capacity. And the problem asks us to plot the molar flow rates of A and B as a function of cumulative volume as we move down the reactor, effectively the same as saying as a function of distance as we move down the reactor, and to also plot the temperature versus volume as we move down the reactor. So what we're going to write is mass balances and an energy balance for the system, and then we're going to account for the volumetric flow rate change due to the mole change and the temperature change using the ideal gas law. So the first part is the mass balance. And what we have here is the change in the molar flow rate of A. So FA represents the molar flow rate, is equal to this rate expression, which I'm calling R1, which is just K times CA. The minus sign is because A is reacting. Now, we could use stoichiometry to account for the products, or we can just write differential equations. Because we're going to solve this numerically, we can just write the differential equations to solve simultaneously, where now we have a plus sign here because we're forming products B and C. And when we have differential equations, we need initial conditions, namely at the inlet of the reactor, where volume is equal to 0. We need molar flow rate of A, which we're going to have to calculate. Molar flow rate of B is 0, and the molar flow rate of C is 0, because the problem says we have pure A coming into the reactor. And we're going to use the ideal gas law. We can certainly write as PV equals nRT, but for a flow system, we're going to write a pressure times the volumetric flow rate is the molar flow rate. It's a total molar flow rate. In general, as we move through the reactor, the volumetric flow rate is the flow rate of the three components, RT over P. For the inlet of the reactor, we're given the volumetric flow rate. There's only A, there's no B and C, so we can calculate the flow rate of A coming into the reactor as the pressure times that inlet volumetric flow rate, so substitute subscript 0 to indicate this, over RT. We'll substitute some numbers in here to get our inlet molar flow rate of A because we need that as an initial condition for our differential equation. We have our inlet molar flow rate of A, which we use as our initial condition. And then we're going to use this equation, which remember is essentially the ideal gas law, in solving to account for the volumetric flow rate change as you move down the reactor. So we have the mass balances. We now need the energy balance. And essentially, if we look at the heat capacities, we can see the heat of reaction doesn't change with temperature because the heat capacities with the stoichiometric coefficients sum to 0. In other words, CPA, where A is the reactant, so we put a minus sign, CPB plus CPC is 0, which means delta H is independent of temperature. And so we can end up simplifying our energy balance. We're first going to write it in general form. Heat capacity of A, heat capacity of B, heat capacity of C. So at any point in the reactor, derivative of the temperature in the reactor with respect to that cumulative volume, that's going to change because of the heat of reaction and the rate of reaction. This is negative, it's negative, so this is positive, so the right side is positive. As you would expect, the temperature is increasing for an exothermic reaction. But we can simplify because of the fact that the heat capacities of B and C are equal to the heat capacity of A, and the flow rate of B is the flow rate of C because of stoichiometry. So we can actually write this left side as just the heat capacity of A times the molar flow rate. And so this then becomes our differential equation for the energy balance that we're going to substitute in to a numerical program to obtain the solution. We're going to need a few other things. R1 is minus KCA. We're going to have to substitute in the value for K, which is given in our problem statement. We're going to have to use this volumetric flow rate equation. We also need the concentration of A. We're going to calculate the flow rate of A. The flow rate of A divided by the volumetric flow rate gives us the concentration. And then we need to enter the values of heat of reaction, heat capacity of A, the gas constant, and the pressure. And we're going to solve these equations all simultaneously. And we're going to, in this case, use polymath as a relatively simple method to solve differential equations. So what I am showing now is the polymath program, where I've written the mass balances, the three differential equations, and their initial conditions. We have to substitute in our starting volume. We call this volume equals 0, and our final volume, 800 liters. The energy balance that I've just written with the flow rate and the heat capacity terms in denominator on the right side to satisfy the format for polymath with the inlet temperature, and then the various parameters that we need, and then the rate expression, the concentration calculation, and the volumetric flow rate calculation. Here are the results from polymath. First, the molar flow rate. So as we move through the reactor, the molar flow rate of A decreases to a relatively low value, and correspondingly the molar flow rate of B increases, and of course this would also correspond to molar flow rate of C. And you'll notice that the rate that FA is decreasing actually becomes faster as we go further down the reactor because the temperature is increasing. So this is a rather dramatic temperature increase, demonstrates what can happen in an adiabatic reactor. We have to be careful as to whether we could realistically run a reactor this way. And with this big a temperature increase, we'd have to worry about additional reactions that take place at the higher temperatures as to whether this would be a good model. But the temperature increase and the molar flow rate increase means that the volumetric flow rate actually increases significantly. Or the other way of looking at it is this decreases what the residence time in the reactor would be compared to isothermal case with no mole change. So the volumetric flow rate starts close to 2, ends up above 6 because temperature expands the gas and we're doubling the number of moles as reaction takes place. And so this is a template to solve adiabatic reactors. If we have multiple reactions, more complicated kinetics, we can just change one or two terms in this polymath program and calculate the profiles of temperature and molar flow rates as a function of distance or cumulative volume down the reactor.